Hello, and today we're going to talk about 3.1 intermolecular forces. Part 1 of the video is going to be ion dipole, 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 and hydrogen bonds. Let's dive in. So the first thing we want to talk about is the difference between intramolecular and intermolecular forces. Intramolecular forces refers to the bonds or the forces that occur that are the bonds. So if you take a look at this right here, that's considered to be an intramolecular force because that's actually the covalent bond in there. Intermolecular forces is the attraction between two different molecules. So if we take a look at H2O, you can see that this dotted line here represents the force of attraction between two different molecules. In this case, two water molecules. So they're basically stronger forces on the intra side because those are generally going to be things like covalent and ionic bonding, while these are going to be a little bit weaker and a little easier to remove. Now, an ion dipole, we talked about in the last unit, has to do with this idea of charges. And so if we define ion dipole, it's basically going to be that force of attraction between the ion and the polar molecule. So for example, we have these are going to be polar. And the reason why they're going to be, in this case, polar molecules, because you have that unequal distribution of charges. So another force that we talk about is that charge between those dipole molecules. So if we put a positive charge in between these dipoles, they're going to be attracted to the negative side. Similarly, on the negative side, you are going to be attracted to the positive side. So that's going to be a force of attraction that's going to occur between different molecules. Here's an example of sodium chloride. Sodium chloride, as you already know, is an ionic bond, and when it breaks apart into its ion form, it creates sodium plus, and when it's surrounded around by water, it's surrounded with the partial negative charges around it. The partial negative charges surround the sodium plus ion, and in the Cl minus, the partial positive charges attract to the Cl minus. So in this case, you see that the chloride and the Na plus ions have this ion dipole interaction. Going back to Coulomb's law, we talked about in the last unit that Coulomb's law is defined as F equals K, which is a constant, times Q1, Q2 divided by D squared. And we talked about how if the force of attraction increases, in other words, that Q increases, your force is going to overall increase. Similarly, if your D decreases, your force is going to increase. So ion dipole forces of attraction increase as the radius decreases. So if the radius is smaller, meaning that these ions are going to be closer together, your force is going to be larger. As the charge increases, so same thing with sodium chloride, if we have something like a magnesium, then the force is going to increase. And that magnitude really is going to increase the polarity of that molecule. So the more that force is, the more polar that molecule is going to be. Now, dipole, same situation. The only difference here is we're talking about two different dipole moments. And in this case, you do have attraction of two dipoles, one on the negative side and the positive side. So if we take a look at a water molecule as an example, they do experience Coulombic interactions as they get close to each other because that force of attraction increases as you get more dipole. So the idea here is that as you're getting more dipole connections, these forces are going to start increasing as you get more Coulombic forces. The orientation is very similarly to what we saw with the ionic solids a while back, but the orientation basically falls under this idea of alternating positive negative charges. So the positive negative charges on the dipole are going to result in stronger attractive forces. In other words, the positive and the opposite force are going to attract. While you're also going to have some repulsive forces, which are going to be a little weaker, which basically allows the molecule to arrange themselves in an alternating positive and negative side. When the positive and negative poles do not line up, then at that point we have repulsive forces, which make them stronger. And so as you can see from here, if you just kind of shift the dipoles a little bit, you could see that the positive charges begin to flip-flop back and forth. And once that happens, you start getting those interactive repulsive forces that you don't want. Hydrogen bonds are going to be defined as anything when you have a dipole-dipole category. So if we take a look at dipole-dipole, ion dipole, these refer to when hydrogens are going to be bonded to the three elements, fluorine, oxygen, and nitrogen. And when they do that, they must have at least one lone pair for them to qualify as a hydrogen. So the definition of a hydrogen bond is a type of dipole-dipole. So if you think about water as an example, water has a dipole in it. And this really has to do with the fact that you're binding to a very highly electronegative element, such as fluorine. And these are going to be a lot stronger than many of the other dipole interactions that we find. So hydrogen bonds, again, making sure that they have at least one lone pair. Question is, why are hydrogen bonds so strong compared to some of the other intermolecular forces? And the answer is the fact that these actually are very polar bonds. So FH, OH, NH are very, very polar. And because these atoms are very small, there's a very high difference in electronegativity, which eventually causes that big difference. So if you take a look at fluorine versus a hydrogen, that difference is really what creates that polarity. The lone pair also increases the partial negative charge on one side. So for example, fluorine here would have very, very high charge because it's got a lot of lone pairs on it, and thus creating a stronger attraction or pull for that hydrogen. So as you can see from here, this really comes back to this idea of electron distribution. Let's take a look at an example for water. Water has H2O, two of these, and you can see water is filled up to the bone here with electrons, with the oxygens, and it forms this bond between the H and the O. That's going to be considered a hydrogen bond. And that hydrogen bond out here is defined as this dashed line with the two lone pairs on oxygen. But to form other H bonds, you would also have to attach other water molecules. And so in this case, what you'll see is H and O, and they create this entire network of water molecules. Now, in this case, what we're throwing here is we're going to throw in some alcohol. So in this case, we're going to throw in methanol. So methanol can also connect itself with water. Even though water can connect itself with these O's, we technically have water here, alcohol, water, and alcohol, or methanol. And that has to do with the hydrogen bonds that it can form with other highly electronegative elements like O. In acetamide, we also have the exact same thing. In acetamide, you can actually put these two together, and the boiling point is about 221 degrees Celsius, which is a very high boiling point because of the fact that you have a lot of hydrogen bonds. And it forms multiple hydrogen bonds with itself. Hydrogen bonds with O, hydrogen bonds with O. Now, ethanol does not form hydrogen bonds. And so if we take a look at, this is actually ethanol, what happens here is this structure does not form. It's because it's bonded to the carbon. And so if you take a look at this molecule, for example, the hydrogen is bonded to the carbon already, right? And so the hydrogen needs to bond with an F, O, or N to form a hydrogen bond. So in this case, we have a little bit of a different structure because although you could say, well, why can't I put an H right here? The problem is that the H is already bonded with the carbon, unlike in the other situations where you can actually open those up. So hydrogen bonds have a situation where the molecules are only going to bond on this graph. So let's take a look at the boiling point. So this is a very important graph that I want you to consider. In period 2, if you take a look at the only molecules that bond here, their boiling temperature for water is going to be very high. But as you get closer down to the bottom where you don't have hydrogen bonds, then at that point the boiling temperature is actually lower. And so as you go across the period, you could see that as you're increasing the number of hydrogen bonds, the boiling point generally will increase as well. So these are only molecules with hydrogen bonds. These don't have hydrogen bonds in here. But as you can see from here that there is a correlation, there's a relationship between boiling point and also the strength of the bonds. Okay, so let's talk a little bit about polarity and strength. So these are all interconnected in the intermolecular force category. And we're going to talk about the high potential energy and the low potential energy. So high potential energy, as a recap, is when you have a very big distance between two atoms. Low potential energy is as they get closer. So again, thinking about in physics, when you have someone on top of a hill versus someone who's coming down, you actually have high potential energy as you're up on the hill. And then you have low potential energy as you're getting a little closer. So molecules which have generally very strong dipoles, have very strong attractions, which eventually pull them together. And because of that, they have a lower potential energy. So basically, they are so attracted to each other that they kind of get stuck and then they have a low PE. So energy must be added to weaken or to break those bonds, which means that you have to provide a lot more energy inside. And so potential energy increases as the molecules move away. So generally speaking, if you're talking about very ionic or very high dipole covalent structures, they're generally going to have very high, very low potential energy because of the fact that they're going to be really close together. So here's an example of a dipole-induced dipole. So again, kind of thinking about this idea with polarity and dipole is that if you have a polar molecule and you have a nonpolar species, you're not going to be able to interact with them because of the fact that the nonpolar species doesn't have those charges. But if you polarize the molecule and you move the charge this way, you can eventually make them stick to each other. And that usually means dissolving. That usually means like you're going to be able to interact in some form. So that's why water is considered to be the universal solvent. It's because of the fact that you're able to dissolve other like molecules that are polar. So dipole-induced dipole refers to the attraction between dipole-induced dipole molecules where there's going to be a stronger magnitude of polarity. And so molecules that have very large dipoles generally have the ability to induce a larger dipole in a non-polar molecule. So again, going back to this slide right here, if this is very polar, I can actually switch the other non-polar species. The strength of the dipole forces also increases when the non-polar molecule has a large electron cloud and is more polarizable. So basically what this means is that if you take two polar molecules, you put them close to each other, they're going to get really, really polar, and you can also swing one of the non-polar sides into a polar region.